Sustain and expansion stresses in piping system, second part. As in the previous video, here again we will see some more configurations and try to calculate the stresses that are considered in calculating sustain and thermal expansion stresses in any piping system as per ASME code B31.3 for process piping. Continuing from the recapitulation of the sustain and expansion stresses equation given in ASME code B31.3, to calculate these components, we have sustained stress equation given as the equation for stresses due to the sustained load such as pressure and weight in the case of process piping as written in code ASME B31.3 2012 edition is given by SL equals to under root of axial and bending stress the whole square plus twice of torsion stress the whole square. So the sustained stress is a function of the axial and the bending stress and the torsional stresses, where the axial stress is given by Fa by Ap into the multiplier factor Ia. Torsional stress is due to the torsional moment divided by twice of the section modulus, and bending stresses in the form of in-plane and out-plane bending moment divided by the section modulus of the pipe. Here the coefficients Ia, It, Ii and I0 are the sustained stress indices. Mi is the in-plane moment due to sustained loads, example pressure and weight. Mi is the out-plane moment due to the sustained loads, that is the sustained section modulus of the pipe. Mt is the torsional moment due to the sustained loads, and Ap is the cross-sectional area of the pipe. Fa, the longitudinal force due to the sustained loads. So this is the sustained stress equation given in ASME B31.3 2012 edition. Now looking at the expansion stress equation, again it's in the same form. The expansion stress SE is again a function of axial and the bending stress and the torsional stresses with the same equations, but herein we will have the parameters that are bounded by the thermal stress, the thermal expansion properties. So as here SA is again the axial force divided by AP, ST is due to the torsional moment, and SB the bending stress is due to the in-plane and out-plane bending moments. Here again the coefficients Ia, It, Ii and I0 are the stress intensification factors, Mi the in-plane bending moment, Mo the out-plane bending moment, and SB the resultant bending stress, Z being the section modulus of the pipe, the torsional moment Mt, the cross-sectional area of the pipe AP, and Fa is the range of axial force due to the displacement strains between any two conditions being evaluated. So this is the expansion stress equation as per process piping code ASME B31.3. Now again herein we will be looking at various configurations. As we have seen the configurations in the earlier video, starting from therein. Here we have stage 3 case A, where the pipe turns back towards x-axis and runs further to a significant distance. So continuing from the previous video, we will try to find out the three basic components of the stresses, the axial, bending and the torsional, as given in the process piping code B31.3, and we will see for this configuration how these stresses are getting calculated in the sustain and the expansion condition for this configuration. So first, let there be no support at any point on the pipe and it be anchored at initial point A. Now in this configuration we don't have any axial stress in the sustained condition. There is a bending stress, and this is due to the weight force acting on each of three legs and various moment arms. The combined moment along x direction is responsible of producing the bending moment and in turn bending stress at anchor point A. So we have the combined loading which is producing the bending stress at the anchor point A. Resultant of moment mx and mz, the direction in which the pipe runs. So the resultant of the moments mx and mz in the axial direction of the bend produces the bending stresses at bend point B and C. So we have bending stresses produced at point B and C, which is the resultant of the moment mx and mz. At bend point B, it is given by the relation mx cos theta plus mz cos theta, which is the component of the x direction moment and the z direction moment, the direction along which the pipe runs. It's the resultant of this x and z direction moment in the axial direction of the bend, and it can be obtained from the relation mx cos theta plus mz cos theta, which can be written as mx plus mz divided by root 2, as theta here is 45 degree for a 90-degree bend. So this is mz, and then we have mx, and these two, the resultant of these two in the axial direction of the bend gives the bending stress when it's divided by the section modulus of the pipe and multiplied by the stress intensification factor. At bend point C, again we have moment along mz, moment along mx, and the resultant of that. This resultant moment multiplied by the SIF with outplane intensification factor in this case, as the bending here is taking place out of the plane. This configuration being anchored at point A tries to move the piping to, or tries to rotate the piping at the bend point outplane direction, out of the plane. So here the outplane intensification factor is multiplied to the bending moment, the resultant bending moment, and when divided by the section modulus of the pipe gives the bending stresses at the bend point. The resultant of moments in mx and mz direction produces the torsional stresses at bend point B and C. Again, the torsional stresses are given by the resultant of moments mx and mz direction. Continuing with this case, torsional stresses is present over here. Now, resultant of moments mx and mz in the direction normal to the axial bending direction of elbow, that is the tangential direction of the bend, produces shear, leading to the torsional stress at bend points. At bend point B, it is given by relation mx cos theta plus mz cos theta, which is equal to mx minus of mz divided by root 2. Herein, we have the negative sign appearing because mz makes an angle of 135 degree with the tangential direction, the shear direction, while mx makes usual 45 degree for the 90 degree bend we have taken. So this is the tangential direction, and here we can see the mz is making an angle of 135 degree with this, and that's why we have the negative of mz in the equation. At bend point C, the equation given is mx cos theta minus of mz cos theta, which is equals to mx plus mz divided by root 2. Here plus sign appears because negative mx makes an angle of 135 degree with the tangential direction, while mx makes an usual 45 degree for the 90 degree bend. So herein we have mz in the negative direction and mx as usual, and then we have the tangential component. So for this condition we have the equation given as mx cos theta minus of mz cos theta. Now, so talking about the expansion stresses, in this configuration we will not be having any expansion stresses, as the system is simply anchored at the point A and it's not supported anywhere, so it's free to move in any direction when it's thermally heated. So no expansion stresses are produced, like no axial stress, no bending stress, and there is no torsional stresses in expand condition. Now moving to a case 3b, wherein let there be a support at other free end, that is point D, without any friction on the pipe, and it be anchored at initial point A. So here what we are doing is that we are providing a support at point D, that is the free end of the pipe, and this support is a frictionless support. Now again, there will not be any axial stress, sustained axial stresses for this configuration. The bending stress, it's approximately same at the anchor point, but it reduces at the bend point. So the bending stresses are reduced because we have added a support at the free end of the pipe. Torsional stresses are again reduced. Now, because it's a frictionless support, we will not be having any expansion stresses. So we have the non-axial, non-bending and the non-torsional stress, as we have seen in the earlier video when the frictional forces were creating resistance to the thermal growth. Herein again, because it's a frictionless surface, there is no such resistance created, and therefore we don't have any expansion stresses. Yeah, we do have the sustained stresses, but it's reduced than compared to the previous condition because of the support provided at the free end. Now, moving to the next case, wherein we will provide, wherein let there be a support at other free end, and this support this time is there with a friction, and let the anchor point be as it is. So this time we are introducing a support with friction at the free end, and we will be seeing the various stresses and sustain expansion condition. Axial stresses, well, none in this case again. Bending stresses remain the same because the frictional force doesn't produce any effect on the sustained stresses. The sustained moments are same, and therefore we have the same bending stresses in sustained condition. Torsional stresses again are same. Well, however, we will have a difference in the expansion condition because now friction is coming into play, and this friction will restrict the thermal movement will be restricted because of this friction, so we will have the expansion stresses produced in this configuration. So axial stresses appears. Axial stress as anchor point is given by Fx divided by Am as earlier, where Am is the mean middle cross section area of the pipe and Fx is the axial force. At bend point, it is given by the relation Fx cos theta plus Fz cos theta. That is the resultant of the x direction and z direction of the force in which the pipe is running. Pipe is running in the x and z direction, and therefore at bend point B, we have the resultant across the x and z direction given by the relation Fx cos theta plus Fz cos theta, and theta being 45 degree over here for a 90 degree bend, we can simply have the bending moment over here as fx plus fz divided by root 2, and this one divided by section modulus and multiplied by stress intensification factor of the bend, we can get the bending stress at bend point B. So herein what's going to happen is that axial stresses in this animation, because the pipe is trying to grow thermally and there is a friction which is restricting the movement of the pipe, we have the stresses generated, axial as well as the bending. Bending stresses also appears. Herein in-plane bending stresses and expansion is developed, which is totally due to the moment produced along the my, that is the perpendicular direction of the plane of the configuration, as the opposing force for the thermal growth are along x and z. So we have a bending stress because of the bending moment in along my direction, my the perpendicular direction of this piping configuration, because the pipe tries to expand in x and z direction. So we have a bending moment in my, and this bending moment along my produces the bending stresses, and this is in plane bending stress, as in thermal condition in the expansion condition pipe is trying to expand in the plane. So we have the bend point, and then my is resulting bending moment which is producing the bending stresses. Well, there isn't any torsional stresses in this configuration. Next, advancing to case 3D, let the other end also be anchored with an anchor at initial point A. So we have now two anchor points, and the both free ends of the configuration are anchored now. And now we will be looking at the sustain and the expansion stresses, and the components are axial bending and torsion, which gives the expansion sustained stresses as per ASME code B31.3. So herein again we don't have any axial stresses. Bending stress is reduced significantly because now instead of a support we are having the two fixed anchor points, which is not allowing the system to bend out plane easily as it was the case earlier where a simple support was provided, or the first case 3A wherein no support was provided. So bending stresses over here because of the anchor point both ends get reduced, and same is the structure for the torsional stresses. So the weight still is acting, but now the bending stress is reduced. Torsional stresses again reduces because of the same reason. Movements along axons are acting, and we have a reduction in the torsional stresses. Well, in expansion case, axial stresses are zero at the anchor point, which was not the case earlier. So we have at the axial point no axial at the anchor point no axial stresses, but they are present at the bend points. In this case, leg AB, BC, and CD all expands thermally due to no net effects force at the anchor point. Axial stress is zero at anchor points. At bend point, again it is given by relation fx cos theta plus fz cos theta, where theta equals a 45 degree per 90 degree bend along the axial direction of the bend. So herein, as no fx force is acting, axial stress is given by fz divided by root 2 because fx becomes 0 and theta equals 45 degree. So the axial stresses for this configuration wherein the both ends are anchored, we have equation fz divided by root 2 to determine the axial stress at the bend point. Now, bending stresses increases significantly in this condition, and there is no torsional stresses. Well, the reason behind the significant increase in the bending stress is that as the both points are anchored, they restrict this configuration to expand as they were expanding in the previous condition where there was a friction support or the frictionless supports in the case 3A and 3B or 3C. So two anchor points are restricting the pipe to expand freely in x and z direction. So we have the increased bending stresses, and this bending stress is again along the plane MY. Moving to a next configuration where for the first time we will be having a vertical leg BC. Next we advance to the fourth stage wherein the pipe rises up to the and turns towards Z axis for significant distance. As in earlier cases, let there be no support at any point on the pipe and it be anchored at initial point A. Well, axial stresses appear at only bend points, that is B and C, in this configuration. For this configuration, we have axial stress appearing in the system in the sustained case. However, there is no axial stresses at the anchor point, but these stresses are away from the anchor points. In sustain, the loading present is only the pipe weight, and this vertical pipe weight is creating an axial stress in the system. So we have the axial stresses being created in the system for the first time in any of the configuration that we have seen earlier in the sustained condition. Axial stress as bend point B and C is given by relation Fy cos theta divided by Am, where Am is the metallic area of the pipe, and as theta equals 90 degree, it is given by Fy divided by root 2 divided by Am. For this configuration, that is without any supports other than anchor, we don't have any My component of movement. So for bending stresses, we'll be seeing which is a maximum at the anchor point A. They are present in the various legs, but it's maximum at the anchor point A for this configuration. And again, we don't have any my component at the moment for this configuration. In sustained case, bending stress is maximum at the anchor point, which is given by the relation mz in this case. So sustained bending stress is maximum and is given by, is because of the moment in z direction, that is perpendicular direction in which the pipe is running. At bend point B, sustained bending stress is obtained by the resultant of axial bending moment and bending moment along z direction given by the relation mx cos theta plus my cos theta the whole square plus mz the whole square by z. So herein at the bend point we have the bending stresses in sustained condition because of the z direction moment, that is perpendicular direction moment of the leg in which the pipe is running, and the resultant direction the moment at the axial direction the moment at the bend point. So mx cos theta plus my cos theta being the moment along the axial direction, and this along with the z direction moment gives the resultant sustained bending stresses at the bend point B when multiplied by the section modulus of the pipe and when divided by the section modulus of the pipe and multiplied by stress intensification factor for the bend. So this is the mz component, the moment, and this is coupled with the axial direction component mx cos theta plus my cos theta at bend point to give the net bending stresses at the bend point B. Thus the net stress is given by, because we don't have my in this particular configuration because there is no support acting except an anchor point at A, it's given by the relation mx cos theta the whole square plus mz the whole square divided by z into stress intensification factor. Now continuing with the same case, torsional stresses is present from anchor point till bend point B. So we will be having the torsional stresses in this configuration only for the leg AB. For sustained case in this configuration, again we know that due to the absence of my component of the moment, torsional stress, which is maximum at the anchor point, is given by mx in this case. So because no my is there, it is given as mx, and if there would have been my, when we would have added a support, it would have been given as a summation of mx plus of my at the anchor point A. So it's totally because of the mx moment that we are having the torsional stresses. At bend point B, torsional stress is obtained by the resultant of axial torsional moment and is given by the relation mx cos theta plus my cos theta divided by 2z. So in the axial direction of the bend, we have the torsional stress. Thus the net stress is given by mx cos theta divided by 2z, as my component is 0 over here. So torsional stresses, net torsional stresses can be calculated by mx cos theta divided by 2z into stress intensification factor for the bend B. Now again, looking at the expansion stresses, as there aren't any support or any friction or any opposing restricting body which is going to restrict the thermal growth of this configuration, we won't be having any expansion stresses. So there won't be any axial stress, there won't be any bending stress, and there won't be any torsional stresses in the expansion condition for this configuration. Now moving towards the next case B, wherein we will be providing a support and that will be with friction at the free end point D. As usual, let the anchor point be at A. And now we will be looking at the different stresses type in the sustain and the expansion case. Well, for this configuration, axial stress is appearing at all points. Initially, when there was no plus y support, it was not acting at the anchor point. Now in this configuration, when we have produced the plus y support, the axial stress is acting at all the points in sustained condition. Again, in expansion condition, there is axial stress produced and it's appearing at all points simply because of the support that is there with the friction. So this friction is restricting the motion, the thermal growth of the pipe, and producing the axial stresses. The relation we are going to just see now. In sustained expansion condition, axial stresses at the various points are axial stress at anchor point A is equal to Fx divided by Am, that is the axial direction of the leg divided by the metallic area of the pipe. Axial stress at bend point B is given by Fx cos theta plus Fy cos theta divided by Am, the metallic area of the pipe. So it's in the axial direction of the bend and the resultant of the axial direction and the resultant of Fx and the Fy forces. So bend point B, we have the force calculation done with the help of the formula just seen. As the leg BC is in y direction, axial stress in the leg BC is given by Fy divided by the metallic cross-section area Am. Axial stress at bend point C is Fy cos theta plus Fz cos theta, that is the resultant along the direction in which the pipe is running, divided by the metallic cross-section area of the pipe. So this is for the bend point C. For leg CD, which is in the z direction, axial stress is there and it is given by the relation Fxz divided by Am, the metallic cross-section area of the pipe. So this is for the axial stresses, which is now present in both the sustain and expansion condition, and the relation to obtain them are pretty much same. However, the guiding force, the guiding factor behind this is very much different. In expansion condition, it is totally pure because of the thermal expansion, because of the alpha delta T and the friction force creating resistance in this expansion path, while in sustained condition it is totally because of the weight that is acting downwards and the pressure in the system. Well, we have not taken pressurized system, so it's totally because of the weight W. Continuing with this case B, we will be looking at the bending stresses. Well, in sustained condition it is maximum at the anchor point A and it's present all over the leg AB, BC and CD. In expansion condition again it is maximum at the anchor point A. When we have support with friction applied at point D, we get My moment component, which was absent in earlier case, wherein we didn't have the frictionless support, or we had the frictionless support, or we were not having any of the support except the anchor point. In this case, because we were having a support with friction along with the anchor point at A, we were having the My component of the moment present. So this My component of the moment will be taken into consideration for calculating the bending stresses at points. Now, bending stresses is maximum at the anchor point, which is given by the resultant of My and Mz in this case. So bending stresses is because of the My component of the moment and Mz component of the moment, and it's the resultant of these two components of the moments divided by the section modulus of the pipe, producing the bending stress of the anchor point A in both the sustain and expansion condition. At bend point B, sustained bending stress is obtained by the resultant of axial bending moment and bending moment along Z, given by the relation mx cos theta plus my cos theta the whole square plus mz the whole square divided by the section modulus of the pipe into stress intensification factor at bend point B. So here, as we have seen this equation earlier, we will now be having My component of the moment adding up into this sustained bending stress formula, and it will give the net sustained bending stress at the bend point B. So it's in the axial direction of the bend, mx cos theta plus my cos theta, and this is coupled with the perpendicular direction moment mz, and then divided by the section modulus. Now at bend point C, it is given by the relation my cos theta plus mz cos theta the whole square plus mx cos theta the whole square divided by section modulus of the pipe. So herein the resultant of the direction and the resultant is in the direction in which the pipe is running, that is y and z, and it is coupled with the perpendicular directional moment, that is mx. So here we see the axial direction of the bend, mz cos theta plus my cos theta, and this is coupled with the mx moment, mx, and thus this when divided by the section modulus, this resultant is divided by the section modulus multiplied by the stress intensification factor at bend point C. We will be having the sustain and the expansion bending stresses. Well, both the sustain and expansion bending stresses given by the same formulation. However, as told earlier, they are because of the different factors. Sustain is only because of the weight, while expansion is totally because of the thermal expansion. In leg BC, that is the vertical leg, the bending stresses is because of the resultant of moment mx and mz. So the two perpendicular moments produce the resultant, and this resultant when divided by the section modulus gives the bending stress at leg BC. And in leg CD, again in the same fashion, the two moments, orthogonal moments, getting combined together to produce the bending stress when divided by the appropriate section modulus of the pipe. Continuing with the same case, torsional stresses. Now, looking at the torsional stresses, they are present in the leg AB and BC. So, they are present in the x direction and the y direction. They are not present at the support point, the torsional stresses, for the sustain and the expansion condition. In both the sustain and the expansion cases, torsional stresses in the leg AB is due to the mx moment. So the direction in which the pipe is running, the torsional stresses is because of that directional moment. So this, in leg BC, it is due to the my moment, and leg CD, there is no torsional stress at all. So in leg BC, it is because of the my, the direction in which the pipe is running. It's because of that moment, and in CD, we don't have any torsional stresses at all in the sustain or the expansion condition. At bend point B, torsional stress is obtained by the resultant of axial torsional moment and is given by the relation mx cos theta plus my cos theta divided by twice of the section modulus of the pipe. Herein, we have the x directional moment and the y directional moment, that is the pipe in which the direction in which the pipe is running. We have the moment along those direction, and these two moments produce the resultant moment along the axial direction of the bend, which is given by mx cos theta plus my cos theta, and this when divided by the appropriate section modulus produces the torsional stress. And at bend point C, it is given by the my cos theta plus mz cos theta, that is the direction in which the bend is running, the y and the z direction, and then the resultant of these two direction moment divided by the appropriate section modulus of the pipe, with theta being 45 in our case. So we have mx cos theta plus my cos theta, the moment along that direction for bend point C, and then z cos theta and my cos theta for the moment along bend point C. So we have just seen various configurations coupled with the previous video. Here in two configuration was discussed, and in previous video we had configuration discussed. So with this, we just try to calculate the components of the stresses that are actually contributing to the sustained and expansion stresses given by the core ASME B31.3 equation, and at bend points how they are calculated, at support points how they are calculated, or at the anchor points how they are calculated. So it was basically the calculations that is done. Now, if when we make both the ends anchored, as we have done in the previous cases, we will have the reduced sustained stresses, because now the system is anchored at the both free ends. The weight will be acting, of course, and that will be producing the torsional as well as the bending stresses, but that will be in a reduced quantum. Well, the expansion stresses, because them being anchored, they will be quite high, as for the reason we have seen earlier. Thus, this ends up with our episode on sustain and expansion stress calculation for some of our basic configurations. So herein we saw how the component stresses of ASME B31.3 code equation appeared in various systems and how they were calculated. Once we know the root cause of the appearance and the calculation factors, we can easily optimize and control our stresses in any of the complex configurations. Optimization of stresses is necessary, as we have seen that more strain we provide, the more stress relieved is the sustained condition, while the expansion condition gets more stressed up. So with the supports, we have less sustained stresses, more expansion stresses. So this optimization is very much necessary. So this balancing and optimization is necessary for any system, stresses to be controlled. And once we know how they are calculated, we can just advance further for the complex system and then break it node wise, and then we can reduce down the stresses. So this ends up with this video. Thank you.